Hi, and welcome to the A+ College Ready webinar on how to do equilibrium and Ksp problems specifically. I just wanted to stop for a second and say, after hearing from the AP people about what the exam is going to look like, this is going to be totally doable. You have 2 questions, more than enough time to answer both of them. You're going to be able to do it on a phone. You're going to be able to do it on a computer. You're going to be able to do it on paper and then take a picture and upload it. So I have complete confidence that as long as you're doing the work at home and doing the work with the teachers virtually, I'm sure you're going to do great on the exam. With that said, let's go ahead and get to what kinds of questions will you see. The first type of question you're going to see is the Le Chatelier shift questions. So given an equation, if you do something to one side, what effect will it have? Will it shift towards products, or will it shift towards reactants, or will it have absolutely nothing to do with it at all? You're also going to possibly see some Ksp calculations. They could ask you for molar solubility, and that just means when you dissolve something in water and it's saturated. So that means as much as can dissolve is actually dissolved. So when it's saturated, how many moles per liter will dissolve? That's the molar solubility. They also could put a little bit of a twist on that and say, hey, what is the molar solubility of this thing when there's a common ion? So for example, what's the molar solubility of silver chloride? Well, what's the molar solubility of silver chloride when there's already some chloride ion in solution? They both work the same way. It's slightly different approaches. And in this webinar, I will try and show you what that looks like. The third type of question you're going to see is, can you write a K expression? And what if you flip the equation? What does that do with K? What if you multiply the entire equation by 2 or by 1/2? How do you do the math with K? The fourth type of question is K versus Q. So are you at equilibrium or not? They give you a set of conditions. They give you a value for K. And they say, hey, by the way, where are you? Are you at equilibrium or not? Which way is it going to shift? The fifth type of question is, what exactly is equilibrium? Can you define what's true at equilibrium? A lot of people have an incorrect sense of what equilibrium is. And then lastly, can you find K given a bunch of numbers? Or can you use K to find out what the equilibrium concentrations are? So they'll either give you numbers to find K or give you K and ask you to find numbers. Those are the types of problems that you'll see. So look at this question and think, which one or ones of the answer choices apply to equilibrium? Now, before we go any farther, I want to show you a quick clip of what equilibrium can look like. Here's an equilibrium situation where you have a parking lot of red cars and blue cars. If we start the reaction, the line in the middle of the graph is 50% red and 50% blue. That's why it looks like one line. But if you notice, for every blue car going over to the red lot and red car going over to the blue lot, that rate of reaction is the same. And we can see that in this graph over here. So this is equilibrium. This is a situation when reactants are equal to products. But that's not always true for equilibrium. So what I'm going to do is I'm going to take the forward rate constant and I'm going to make the forward rate from blue to red. I'm going to make it go faster, and I'm going to make the red cars going back to blue a little bit slower. And this time I'm going to start with all red cars. So let's see what happens. In the beginning, there is no forward reaction. It's all reverse. But we end up into a place where there are 5 blue cars and 15 red cars. This is equilibrium because the forward rate is equal to the reverse rate. notice that the concentration is not the same. The number of blue cars is smaller than the number of red cars. So let's try it again, except this time let's start it with all blue cars and no red cars, but leave the reaction rates, this one bigger and this one smaller. And again, we get to about the same point. This is equilibrium because the forward and reverse rate are the same. This is equilibrium. So the equilibrium state is a function of which one goes faster, the forward rate or the reverse rate. And we call equilibrium the point not where the two amounts are equal, but where the rates are the same. The rate of the reverse is equal to the rate of the forward. So let's look at an actual chemical reaction. We see some of the reactants from A turning into products in B, and we see some of the products in B turning into reactants in A. We reach an equilibrium state where, if you notice down here, Q is equal to K. So when Q is equal to K, we say we're at equilibrium. The number of particles in the reactant side and the product side are remaining the same, and the rates of reaction, forward and reverse, are the same. So I can get to that same point by starting out with all product or starting out with all reactant. As the reaction proceeds, you can see that it goes from being all reactants to that same 6 reactant particles and 14 product particles. So it doesn't matter where you start with, the ratio of products to reactants will always be the same. And that's why K is an equilibrium constant. It doesn't change. What is the ratio of products to reactants? So if we go back to our problem, A is not true. I mean, it can be true, but it's not always true for equilibrium. The reaction never stops. In fact, oftentimes they say that equilibrium is microscopically dynamic, meaning it's still happening, but macroscopically static, meaning it doesn't look like anything's happening if you approach it from far away. It looks like the number of cars in the parking lot isn't changing, even though the cars are still going back and forth. C is the correct answer. D, when K is equal to 1, that suggests that the amount of products and reactants is the same. So that can be true, but it's not necessarily always true. And when Q is equal to K, that is equilibrium. So the correct answers here are C and E. So here's a problem I just dreamt up, I made up, to help everyone understand what equilibrium problems you might see. If you take some iron ion and you mix it with some colorless thiocyanate ion, you will get a complex ion that turns reddish brown. And if you look over here to the right, you'll see a test tube with the iron solution, and here's where that thiocyanate got dropped in there, and it's being dark red. So we can measure the amount of red using spectroscopy. We can use Beer's law to say, ooh, I wonder how much of that red stuff there is. So sometimes they'll take this kind of a question and couple it to a Beer's law, just like we did in the kinetics thing with the blue dye. So here comes a Le Chatelier shift. Adding solid iron nitrate would cause what change? Well, this iron nitrate would cause iron ion to be added to the left-hand side. And if I add iron ion to the left-hand side, that'll cause a shift to the right. And so if I add something to one side, it shifts towards the other side to reach a new equilibrium. And the change you would notice is that the two would become more reddish brown. Now, increasing temperature would cause the absorbance to increase, decrease, or stay the same. And oftentimes they will ask you to circle the right answer. Now, this year is going to be special because you're going to be doing it on paper. So I'm guessing that they're going to ask you to make a claim. So the first words out of your pen should be either increase, decrease, or stay the same. If you look at the equation, delta H here is less than 0, which means it's a negative delta H. Negative delta H means that it is exothermic. So that means when the reaction happens, that we're going to create energy in the form of heat. So that means energy is a product because delta H is negative. So if you increase temperature, would it cause the absorbance of the solution to increase, decrease, or stay the same? So if we add something to one side, like adding heat to increase the temperature, if you add it to one side, then what does that cause the equation to do? It would cause this equation to shift to the left, and if you added energy to this, some of that reddish brown would go away and become more light yellow and colorless. So that means the absorbance, if it's less reddish brown, would decrease because there'd be less reddish brown in there. So adding temperature would cause it to shift towards reactants, making it less reddish brown and decreasing the absorbance. They might ask you, here's a value for K for this equation. What would the equilibrium constant be for the following equation? So they give you a value for K, and they say, look at this equation. Well, what they're going to ask you to do is compare this equation that they're showing you to the original equation. So if we look back at the original equation, what's the difference between the top equation and the bottom equation? And what they've done is they have flipped it and they've multiplied it by 2. So the new K for this bottom equation down this means they flipped it, so it's going to be 1 over the old version of K, so 0.333. So we inverted it because they flipped the equation, and they multiplied it by 2, which means we're going to square the old value of K. So if you multiply it by 2, that 2 gets applied as an exponent. If you flip an equation, it would be 1 over the old value for K. That's the kind of question that you can expect to see on the AP exam in terms of some simple stuff that they would have you do. Let's look at another sample. This comes from an actual FRQ. So let's see what they asked you to do. MgOH2, they give you the value for Ksp, and they want to know the number of grams of MgOH2 that is dissolved in 100 milliliters of a saturated solution. The key here is saturated solution. So what they want you to do is find the molar solubility. When you're looking for molar solubility, you're saying, I'm going to add enough solid so that it will all dissolve and yet still leave some on the bottom, because that's true of a saturated solution. So you have some particles that are solid and some particles that are dissolved. All you have to figure out is how many moles dissolved divided by the liters of solution. Once you've found the molar solubility, then figure out how many grams there are in 100 milliliters. So let's see how you would do that. Anytime you have a Ksp or an equilibrium problem of any kind, when in doubt, ice it out. To build your ice or rice table, what you're going to have to do is first have an equation, which we have, and then you're going to put ICE down the side. I means initial, C means change, and E means what is the concentration at equilibrium. So for magnesium hydroxide, when you first dissolve it, how much magnesium and hydroxide is there? 0. So we have 0 magnesium and 0 hydroxide. The change, we know that the magnesium ion, since it started at 0, has to increase by some amount x. And the reason why it's 1x or just x is there's only one magnesium. Meanwhile, the hydroxide will increase by some factor 2x, because for every one magnesium that dissolves, you'll get 2 hydroxides. So that goes up by a factor of 2x. So at equilibrium, we just combine these two. You started out with 0 plus x equals x. We start out with 0 with the hydroxide plus 2x is 2x. And then all we have to do is try and plug in and solve. The Ksp expression is going to be the magnesium ion concentration times the OH concentration squared. I plug in the x from the ice table. I plug in the 2x from the ice table, and it becomes 4x squared, and I get that the Ksp is equal to 4x cubed. I plug in the value given to us in the problem. So the 1.8 times 10 to the negative 11th there gets transferred down here, is equal to 4x cubed, and I find x. X is the molar solubility. What is the concentration of the magnesium hydroxide when it's dissolved? So all I have to do is take that molarity and use it to solve the rest of the problem. So I knew I had 0.1 liters because it told me it was 100 milliliters. I know the concentration is 1.65 times 10 to the negative 4th moles per liter. That's what we just found for x. And I know that each mole, it was given to us in the problem, is 58.32 grams. So if I look back up here, that 58.32 grams per mole is given to us in the problem. The 100 milliliters is given to us in the problem. And we get an answer of 9.6 times 10 to the negative 4th. Now here's the beautiful thing. Even if you messed up above, if you had found an answer, let's say you did 2x quantity squared is really 2x squared. You made a mistake. That's wrong. If down here you would solve for 2x cubed, a lot of times on the AP exam, when you plug in a wrong number from up above and you use it because you think it's right, you can still get a point. Even though you have the technically wrong answer, you use the answer from before and applied it in the next step to see how many grams you'd make. In other words, never give up on a problem. Use your ice table or rice table, find a value for x, plug that in to see if you can solve the rest of the problem. There is a part B to this question, and I just kind of wanted to show you how the AP exam will give you something like Ksp and then ask you to do a little bit more with it. So we've just talked about the solubility of Ksp, and they gave you this value in here of the lattice energy of magnesium hydroxide and strontium hydroxide. Explain why in terms of periodic properties and Coulomb's law. So we know how they want us to argue, but what do they want us to argue about? They are telling you that the lattice energy of SrOH2 is less than the lattice energy of MgOH2. So that's their claim. The claim is that the lattice energy of SrOH2 is less than the lattice energy of MgOH2. That's given to you. They've even given you some evidence down here where they're telling you, hey, here's the data that backs up this claim, and they want you to explain why. So this is just like claim evidence reasoning that you may have been practicing in other classes. So let's see, how would you go about doing this? Well, Coulomb's law, for those of you that have forgotten, Coulomb's law is a function of how far apart two things are and how big the charge is, Q1 versus Q2. So the equation is the force or the energy is somehow related to the charge of one ion times the charge of the other ion divided by the radius. So our claim is that the lattice energy of strontium hydroxide is less than magnesium hydroxide. There's no need to repeat that. The evidence 2300 is less than 2900. Also, no need to restate this. That's already given to you in the question. So since it has to do with radius and charge, we need to run over to the periodic table and see what the periodic table tells us about magnesium and strontium. Magnesium and strontium both have a charge of +2 because they're in group 2. Now, magnesium and strontium, they're ions. So the magnesium ion looks like neon. It loses 2 electrons and takes on the noble gas configuration of neon. Strontium also loses 2 electrons to become a +2 charge, and it looks like krypton. So in terms of our arguments, we need to be talking about how far away these things are and their charges. Well, magnesium and strontium are both +2. If they're both +2 and hydroxide is the same in both of them, then it's not about charge. We're not worried about the Q1, Q2 part of Coulomb's law. We're worried about the R. So how can we have this argument about this is why strontium hydroxide is less than magnesium? Let's talk about electron configurations. The magnesium has 2 occupied energy levels. Magnesium looks like neon. Neon has 2 occupied energy levels, whereas krypton down here, it has 4 occupied energy levels. So you want to just go back and say magnesium ion has 2 occupied energy levels like neon. Strontium ion has 4 occupied energy levels. Therefore, the larger radius of strontium gives it a smaller lattice energy than magnesium. Or the smaller radius in magnesium gives it a greater lattice energy than strontium. Either one is a good way to explain what you mean. But this is how AP is tying together the knowledge that you've learned all year. Yeah, KSP is its own thing. They can turn around and ask you a question from previous content. This is another FRQ from the past, and this one is very, very recent. They give you the equation. No need to write an equation. They give you a value for delta H. Notice that delta H is positive. A 0.1 mole sample of pure bromium chloride is placed in a 2-liter container. Eventually, the system reaches equilibrium. Calculate the air pressure in the container before equilibrium is established. Well, this is one of those questions that's asking you previous content. How would you find pressure with that information? Well, you're given moles, so don't be afraid to circle things and go, oh yeah, I know what moles are. So I'm given moles, I'm given volume, and I'm given temperature. So I ought to be able to plug into the ideal gas law, PV equals nRT, and find pressure. Write the expression for the equilibrium constant. After the system has reached equilibrium, 42% of it is decomposed. Determine the value of KEQ. So you've got several things in here that are point-worthy. The goal is to get them all right. Now, maybe you don't get them all right, but don't ever leave one blank. Let's go ahead and try every single question, because the best way to miss one is to never answer it at all. So I'm going to plug into the first one. I'm just using PV equals nRT. Now, I found it in atmospheres. You could have found it in torr. You would just had to use a different R value. So the answer comes out to be 1.22 atmospheres. That was part D. Part E. The equilibrium expression would be the bromine concentration times the chlorine over BrCl squared. And that just comes from this equation. You have the products over the reactants. Whatever the coefficients are become the exponents. Or conversely, you could have used pressure, the pressure of the bromine, the pressure of the chlorine over the pressure of the bromine chloride squared. Same thing, except instead of molarity, you use pressures. When in doubt, ice it out. So at the very beginning, what do we know? We know at the very beginning that the bromine chloride had a pressure of 1.22. Where did that come from? That came from the answer you just wrote down up here. It asked you what was the pressure originally before equilibrium is established. So you take your answer of 1.22. If all we have is reactant, that means there's no product whatsoever. So what's the change going to be? Well, the bromine chloride will go down by some factor, and the bromine and chlorine will go up by some factor. Now, how do we know that the products go up? Well, because they were starting at 0. They can't go down. They can't be negative. So when you start with 0, the only way it can go is up. So then we just fill in the rest of the table. This would be 1.22 minus 2x. This would be 0 plus x. And this would be 0 plus x. I'll explain where these numbers come from in just a second. The problem tells you that 42% of the original pressure decomposed. In other words, it's telling you how much it decomposes. The minus 2x is 42% of whatever you started with. So what is 42% of 1.22 atmospheres? 0.51 atmospheres. So that tells you what the change in BRCL is. This would be minus 0.51 atmospheres underneath the bromine chloride. Well, if you know that that loss is 0.51 and you also know it's 2x, then we can find the value of x. Because if it goes down by some factor 2x, that's equal to 0.51 atmospheres. That means x equals 0.26 atmospheres. So if we know that x is 0.26, then we can solve for the equilibrium expression where we put 0.71 in for the products, square it because that's the expression, 0.26 and 0.26, and you'll get a value. Now, this was done with pressures. If you were crazy and you like to do a lot of work, you also could have taken the number of moles and you could have worked it out saying 42% of the number of moles decomposed, and you could have found it that way. And guess what? The answer would have been exactly the same. So 3 parts to the question, can you get most or all of the points? Part D, easy, just kind of stoichiometry. Can you do part E, writing an expression? Everybody ought to be able to do that. Part F, when in doubt, ice it out. Build yourself an ice table, see what there is to see, and see where you can go from there. Here's an example of an FRQ from the past that would have to be modified for what we were going to see on the exam on May the 14th. So we have NO plus NO2 makes N2O3. And then they told us something about delta H, delta S, and delta G. Now in a normal year, they would expect you to be able to find the value of K given the value of delta G. In fact, that equation is right there on the exam reference sheet. But this year, delta G is not going to be tested. We don't have to worry about delta S, the change in entropy, and delta G, the Gibbs free energy. So how did they used to want you to solve this problem? They would want you to plug into this equation and find an overall answer. Now, obviously, this is not going to happen this year. So what might they do to ask you the same kind of question? They might turn around and say, the K value is such and such. What does that tell you about the reaction? Does it favor products or reactants? So they could have said the K was 0.70, because that's actually what it is. If K is 0.70, then they might say, does that favor products or reactants? Explain why. Well, you know a K greater than 1 favors products. A K less than 1 favors reactants. So this one would favor reactants. At equilibrium, there will be a greater concentration of reactants than there would be of product. Part II, could you solve that? if both PNO and NO2 are at 1 atmosphere, will the pressure of N2O3 at equilibrium be equal to 1 atmosphere? Well, if you look at it, this becomes a limiting reactant problem. If you have 1 atmosphere of the NO and 1 atmosphere of the NO2, then that means when they react together, they will only form 1 atmosphere of the N2O3. And that's just from the stoichiometry of the problem. 1 NO gives you 1 N2O3. Will the pressure of N2O3 be equal to 1 atmosphere? Well, in order for it to turn into 1 atmosphere, this would have to have an equilibrium far to the right. In other words, it would have to have a really big K, a K value that is exceedingly large, really bigger than 1. And we know that from the problem before, let's say they told you K was 0.7, that wouldn't be possible. So let's see how they actually went about solving this problem. When they say, is it possible or not, you can say disagree. If 1 atmosphere of it is made, then all the reactant would have had to been used up. K would have to be very large. But since K is less than 1, there should be more reactants than products. That is a perfectly acceptable way to explain this. They then go on to say, the student hypothesizes that increasing the temperature will increase the amount of N2O3 in the equilibrium mixture. Indicate whether you agree or disagree with the hypothesis. Justify your answer. Well, this is not an ice problem. This is an equilibrium shift problem, a Le Chatelier problem. So, what do we know about the delta H for this equation? We know that the delta H is negative 40.4 kilojoules, which means that energy here is a product. So we know that the energy is a product and it's exothermic. So let's go back to the question. Increasing the temperature will increase the amount of product. Well, if I increase the temperature, I'm adding a product, and adding a product will cause a shift back towards reactants. So adding a product will cause a shift back towards reactants, which means the N2O3 will become less concentrated because some of the N2O3 will turn back into reactants. Let's see if that was enough. I disagree. Delta H is negative. Energy is a product. Increasing the temperature causes it to shift towards reactants. N2O3 will decrease. I got the point. Now, on the AP exam, they're probably going to give you 1 point here for saying disagree, and then 1 point down here for all this reasoning. Another Ksp problem, but this one has a little bit of a twist. Write a balanced chemical equation for the dissolution of it in pure water. So in other words, when it dissolves, what does it look like? Calculate the molar solubility in 0.1 molar calcium nitrate. Well, here's my balanced equation. Notice I don't have to have states of matter, but it does have to have the right ratio. 1 calcium ion for every 2 hydroxide ions. So the most important thing is that you know they're ions and you know that there's a ratio of the positive ion to the negative ion. 1 point. Now, how do you calculate the molar solubility in 0.1 molar calcium nitrate? Well, when in doubt, ice it out, but you don't really need to even ice it out. Typically, we would say the Ksp is equal to the calcium ion times the hydroxide ion squared. Normally, the calcium would start at 0 and the hydroxide would start at 0. But this time, that's not true. This time, the calcium doesn't start at 0. This time, the calcium starts at 0.1. So instead of starting with 0 amount of calcium, there's already calcium in solution. It works exactly the same way. You could still build a rice table, but instead of starting with 0 of it, you're starting with 0.1 of it because that's what this is telling you. I already have some calcium ion in solution. So we know that the calcium is going to go up by some factor x. We know that the hydroxide is going to go up by some factor 2x. Here's the Ksp value, the 0.10 plus x, the 2x quantity squared. Now, here's the important thing. If you look at this and go, I'm going to have to use the quadratic equation, you're right. But if you have a really fancy, expensive calculator, you're going to be able to get more points than someone who doesn't have as much money and whose calculator doesn't do the quadratic. So what do we do with this? Well, go back and look at the value of the Ksp. This Ksp is so small that hardly any of it's going to dissolve. The Ksp is so tiny that not very much ion will be made. So if you already are starting out with 0.1 of it, and it goes up by some very small factor x, then we say that's pretty much the same thing as 0.1. In other words, 0.1 plus x is pretty much equal to, and I say this is like 2 strips of bacon, 0.1. And what that tells you is that the change is going to be so small it just doesn't matter. So if you're thinking that you need to lose a little weight and you decide to pluck one eyebrow hair, is it going to be enough of a difference? No. It's such a small difference it doesn't matter. For the 2x squared, it is important because how much hydroxide did you start with? You started with 0. Well, if you started with 0, any change at all is immensely huge. So even if the OH goes up by just a little bit, it's still important. So we can simplify the math by saying instead of 0.1 plus x, make it just 0.1. Now we can solve for x, and we'll get an x value of 0.0018. Now, a couple points from the rubric. 1 point is earned for the correct stoichiometry and setup. The stoichiometry is the idea here that it's 0.1 plus x and 2x. The idea that for every 1 calcium, there's 2 hydroxides, and that you can plug it into the Ksp expression. And then 1 point for the final answer. So you would say that the molar solubility is 0.0018. The one we did previously was magnesium hydroxide, and it started with 0 of the magnesium and 0 of the hydroxide. The only difference here is this one started with some calcium ion already. As you read the question, you're like, I'm not even sure what it's asking. Considering the value of K, determine the concentration of the barium EDTA complex ion in the 100 mils of solution. Justify your answer. Well, we talked about this before. This is an example where they give you the value for K, and they're saying, hey, what do you think about it? Well, K here is not just greater than 1, it's 77 million. This is a K that's enormously large, so that, in fact, all of the reactants are going to turn into products. So this is not really a K problem so much as this is a stoichiometry problem. If you've got 50 mils of 0.3 molar and 50 mils of 0.2 molar, how much product will get made? Then it says the solution is diluted with distilled water. After equilibrium has been reestablished, is the number of moles of barium greater than, less than, or equal to the number of moles present in the original solution before it is diluted? So let's see if we can answer part A. K is really, really large. It goes to completion. Barium is the limiting reactant. The barium is 0.2 molars, whereas the ETA is 0.3 molar. So you're going to run out of the barium nitrate first. The concentration of barium when the solutions are first mixed, but before any reaction takes place, and all they're doing is saying it's 0.2 molar divided by 2 gives you 0.1 molar. The reason why we divide it by 2 is because we basically diluted it by a factor of 2. So the barium was 0.2 molar. We divided it by 2 because we added an equal amount of another chemical. So basically we diluted the barium in half because it was 50 mils of each. So if it goes all the way to completion and the barium ion is 0.1 molar, then the equilibrium concentration also has to be 0.1 molar. This was a pretty hard question to get right, but if you think about it, they're giving you the clues of K is really big. Now, how would you do part B? It's diluted with a bunch of water to 1 liter. That's going to cause a change in things. So what happens to the concentration as it reaches equilibrium again? So you could argue this 2 different ways. You could say the barium EDTA complex ion will break apart to reestablish equilibrium, or you could look at Q versus K. So Q is going to be products over reactants, and the reason why they have the 1/10 in there is because it went from 100 milliliters to 1 liter. So they're suggesting, hey, by the way, we're diluting it basically by a factor of 10. So if we put 1/10 the value here, 1/10 the value here, and 1/10 the value there, then you get a value for Q of 10 times whatever the old K was. Since Q is greater than K, or K is less than Q, then we know it'll shift to the left. And since it shifts to the left, that means some of the barium EDTA complex ion will break apart into barium ions and EDTA ions. One more shot at how they layer these questions together so that you can get points from lots of different content areas. A student claims the reaction is a redox reaction. Is it correct or not? You can do that. Assign oxidation numbers, see if they change. Calculate the mass in grams of sodium chloride needed to produce 3 grams of HCl. So, to get 3 grams of that, how many grams of that does it take? That's just a stoichiometry problem going from grams to grams. Easy peasy. These two things are combined in a 10-liter vessel and allowed to reach equilibrium at 400 Kelvin. The initial pressure of the CH3OH is 0.25 and HCl is 0.6. Does the total pressure increase, decrease, or remain the same when you go to equilibrium? Justify your answer in terms of the reaction stoichiometry. So let's not even try to do math with it. Let's just look at the problem. How many moles of gas are there on the left? 2. Look over on the right. How many moles of gas are there on the right in our balanced equation? 2. So no matter how you mix it together, if you have 2 moles of gas on the left and 2 moles of gas on the right, there will never ever be a production or loss of gas particles. You'll still have the same number of moles. So the pressure will stay the same because you're not producing any more gas, or you're not producing less gas than there were on the reactant side. So the stoichiometry tells me that at equilibrium, the pressure will stay the same. Considering the value of K, calculate the final pressure of HCl. So this is the time when they're giving you a value for K and asking you to find the equilibrium pressure. All right, so let's see how they actually worked on answering those questions. It's a redox reaction. No, the student is not correct. I assigned all the oxidation numbers and none of them changed. Then it's not a redox reaction. Done. Calculate the mass in grams. 3 grams of HCl, using the molar mass from the periodic table, using the balanced equation, using the molar mass of NaCl from the periodic table, and you get a final answer of 4.81. Now, for the equilibrium part of it, let's see what they did. They're both combined in the reaction vessel. Does the total pressure increase, decrease, or remain the same? The pressure remains the same. 2 moles of gas produce 2 moles of gas. Pressure doesn't change. Boom. Got the point. Using the value of Kp, calculate the final pressure. So when in doubt, ice it out. You can say, I got 0.25, I got 0.6, this is 0, and this is 0, because they didn't mention having any CH3, Cl, or H2O in the vessel. You know that the reactants go down, the products have to go up because you started at 0. You know minus x, plus x, plus x. You can determine that the x here is 0.25. Now, why are they assuming that there's going to be 0 of the CH3OH? Well, if you go back and look at the value for K real quick, the value for K, if you go back and look at the value of K real quick, K is exceedingly large. It's 4,700. This is much greater than 1. Since it's much greater than 1, then that means the reaction really goes to completion. Most all of the reactants turn into products. So what it's saying is, who's the limiting reactant? Is it the CH3OH or the HCl? Well, from the chemical equation, you know that it's a 1-to-1 relationship. We're going to run out of the CH3OH first, so it's going to end up being 0 at the end. That means X has a value of 0.25 because we're going to use up all of the 0.25. That means I can calculate the HCl by subtracting 0.25. I can calculate the CH3Cl, and I can calculate the concentration of water vapor because it is also the value of X. You can go through there and find the equilibrium pressure of each one, but it only asks you for the equilibrium pressure of HCl. Their parting shot on the question, final partial pressure of CH3OH at equilibrium is very small, but not exactly 0. Do you agree or disagree? When K is exceedingly large, for all intents and purposes, there is no reactant remaining. However, we know that there has to be some reactant left because it's an equilibrium state. Now, is it enough to worry about? No. In fact, the answer here is 3.8 times 10 to the negative fifth. So if we actually plugged in here the value for Kp, we plugged in the values from the ice table of 0.25 and 0.25 and 0.35 from above, you could solve for the partial pressure of CH3OH. You could make the argument of Kp is really, really big, but some have to exist. You could do that. Even if you didn't get this final point, realize you get all these points from answering this question. The stoichiometry, the redox reaction, does it increase or decrease, calculate the partial pressure, and the ending point. Lots of ways to find points here. I will leave you with a funny chemistry cat meme. Hopefully, that gives you enough of a basis to understand what kind of equilibrium problems might they give you on this AP exam coming up in May. See ya!